Imagine this. Your super fast processor, the brain of your whole system, is just sitting there, waiting, starving, basically. Why? Because its lifeline memory just can't feed it data fast enough.
It sounds dramatic, but it's really the reality we're facing now.
Yeah, and it's not just about speed. This memory bottleneck is silently eating up, get this, over half of your server hardware budget.
It's a staggering cost, often completely overlooked. It's holding back everything, especially the big AI models and complex systems you might be working on.
Welcome to AI Paper Podcasts. We're the place where we break down the latest research for you.
Giving you that insider's view.
Today we're diving deep into a really fascinating paper. It's from Peijing Li and a team from Stanford, Microsoft Research, and others. The title, Towards Memory Specialization, a case for long-term and short-term RAM.
And this isn't just some minor tweak they're proposing, it's a fundamental rethink of computer memory.
Absolutely essential for anyone pushing the limits in AI. Okay, so let's jump right into the core of it for a quick summary. The paper basically says our go-to memory types, SRAM and DRAM, they've pretty much stopped getting better at the rate we need. They've maxed out their scaling.
Right. And this isn't just a small technical issue. It means memory is now the #1 drag on performance, power consumption, and cost. Like he said, over half the server hardware cost. It's a genuine crisis.
So what's the fix? The paper argues we need a totally new approach. Forget the simple memory hierarchy we're used to.
Exactly. They're advocating for truly specialized memory architectures, tailored to how data is actually used, not just one size fits all.
And here's the really cool part. They propose two brand new classes of memory. First, long-term RAM, LtRAM. Think of it for data that sticks around, mostly gets read, not written over constant.
Persistent stuff.
Right. And then there's short-term RAM, StRAM. This is for the quick stuff, data that's accessed a lot, maybe, but has a really short lifespan, gets tossed out quickly.
Transient data. So connecting this to the bigger picture, it's all about designing systems that are way more efficient and scalable.
Especially critical, like you said, for AI. Those workloads are incredibly memory hungry.
Aligning the memory to the job it needs to do, that could unlock huge gains in performance and, crucially, cost savings.
Okay, so to really get why this proposal is so, well, radical, let's quickly sketch out the memory landscape we have today.
The standard setup.
Yeah. Typically, you've got this hierarchy, right? Like layers. Closest to the processor chip itself, you have these tiny, super fast SRAM caches. L1, L2, maybe L3.
Right on the silicon. Very fast, very expensive per bit.
Then a step further out, you've got your main system memory, which is usually off-chip DRAM. Much bigger capacity.
The workhorse memory.
And then way out, you've got your permanent storage NAND flash SSDs, maybe hard drives still, for the really long-term stuff.
That basic structure has served us well for a long time.
It has. But let's quickly refresh on SRAM versus DRAM, because their limitations are really the heart of the problem here. SRAM, static RAM.
Yeah.
Super fast.
Blazing fast. Uses 6 transistors for each bit of data.
And it holds its state statically, as long as it has power. No refresh needed.
Which makes it perfect for those caches right next to the CPU cores.
But the downside. Those 6 transistors take up space. It's not very dense, makes it expensive, hard to build really large SRAM pools.
Exactly. Then you have DRAM, dynamic RAM. That's your main memory workhorse because it's way denser.
Just one transistor and one tiny capacitor per bit, much smaller.
But that capacitor, that's the catch. It stores data as an electrical charge, and that charge leaks away pretty quickly.
Meaning it constantly needs to be refreshed, rechanged, essentially.
Right. Think of it like constantly topping up millions of tiny leaky buckets over and over. For DDR5, it might be every 32 milliseconds or so.
And that refresh process, it burns a ton of power.
Huge amounts. And it's happening constantly whether you're actually using that data or not. For a lot of data just sitting there, it's pure waste.
So this brings us to the stark reality check in the paper. Both SRAM and DRAM have basically hit fundamental physical limits. The scaling party is kind of over.
Yeah, they've stopped getting smaller, faster, and cheaper at the pace we desperately need, especially for AI.
Let's look at DRAM. The paper shows, I think it's figure 1A, how the price per gigabyte has just flattened out over the last, 15 years?
It's pretty much stagnated. Yeah, technically maybe you could make smaller cells, but the manufacturing gets incredibly difficult and costly, especially shrinking those capacitors reliably.
And even advanced packaging, like HBM, high bandwidth memory, where they stack DRAM dies.
That helps with bandwidth, definitely. But it has its own density limits. You typically see maybe 16, perhaps 20 dies stacked. Pushing beyond that gets really complex and expensive fast. Doesn't solve the fundamental cell scaling issue.
And SRAM, same kind of story, right? Figure 1b in the paper shows its cell size hasn't really shrunk much since we hit the 7-nanometer node.
Exactly. It's not just manufacturing, it's down to the physics. Trying to shrink those 6 transistors further while keeping them working correctly, balancing their sizes and voltages, especially at lower power levels, it's just incredibly hard.
The impact of this scaling slowdown, it's massive, almost alarming. The paper really drives home that memory is now the dominant cost factor in data centers. DRAM alone, over half the server hardware cost.
It's flipped completely. What used to enable performance growth is now the main thing holding it back. So many cutting-edge applications, especially in AI and machine learning, are becoming memory-bound. They're waiting on memory, not the CPU or GPU.
You hear about things like LPDDR or HBM.
Right, and those packaging innovations are important. LPDDR gives you lower power, higher bandwidth, great for mobile or integrated systems, though it's usually soldered down, not modular.
And HBM gives you that massive bandwidth boost through 3D stacking.
Yeah, using silicon interposers. It's complex, expensive technology, but essential for high-end GPUs right now. But, and this is the key point the paper makes,
They don't fix the underlying problem.
exactly. They offer different trade-offs in performance, power, and cost, but they don't change the fact that the basic SRAM and DRAM cells themselves aren't scaling anymore. They're performance accelerators, maybe workarounds, but not a fundamental solution to the scaling crisis.
Which brings us back full circle to the paper's big idea, moving away from this one-size-fits-all hierarchy towards specialized memory.
Using the right tool for the job, tailored to the workload's specific data access characteristics. That's the core philosophy.
But wouldn't that make things incredibly complex if you have all these different memory types?
That's a great question, and that's where their abstraction strategy comes in. Instead of forcing software developers to deal with, 10 different weird memory technologies directly.
Which would be a nightmare.
Total nightmare. They propose boiling it down to just 2 new logical classes that sit alongside SRAM, DRAM, and NAND. Short-term RAM, STRAM, and long-term RAM, LtRAM.
Okay, so a manageable interface. You get the benefits of specialized hardware underneath, but software sees these 2 broader categories.
Precisely. It gives system designers and operating systems a way to optimize placement without exposing every single gory detail of the underlying device physics.
All right, let's dig into these 2 new kids on the block. Table 1 in the paper lists them alongside the familiar ones. First up, LtRAM, long-term RAM. What's its deal?
LtRAM is designed for data that, lives for a long time, minutes, hours, maybe even longer. And critically, it's data that gets read way more often than it gets written.
Like reference data.
Exactly. Think of it as a super efficient archive for stable information. Its main goals are high read performance and really low energy consumption, especially static power.
Okay, so what's the trade-off?
It accepts that writes might be slower, cost more energy, and maybe the memory cells themselves won't last as long if you write to them constantly. Lower write endurance.
Makes sense. And what kind of actual memory tech could be used for LtRAM?
We're looking at emerging non-volatile memories. Things like RAM, resistive RAM, MRAM, magnet-resistive RAM, FRAM, ferroelectric RAM, or maybe even some clever variants of DRAM designed to hold their charge much longer, minimizing refresh.
And the use cases. Where would you use LtRAM?
Prime candidates are things like machine learning model weights during inference. They're huge, read, constantly, almost never change.
It's a perfect fit.
Also core operating system code pages, hot instruction paths and programs, or maybe large, relatively static data tables and databases, anything read-heavy and long-lived.
Okay, got it. Now the other one, STRAM. Short-term RAM. You called it the whiteboard earlier.
Yeah, I think that fits. STRAM is for transient data, stuff that's maybe accessed really intensely for a brief period but has a very short lifespan, often less than a second before it's just thrown away.
So speed and endurance are key here.
Absolutely. Needs fast reads and writes symmetric performance, needs incredibly high endurance, ideally unlimited because it might get overwritten constantly. And low energy cost per operation is vital.
But holding the data for a long time, not important.
Not really. Retention isn't the priority for STRAM. It's okay if it needs frequent refreshing, as long as the active energy is low.
And the underlying tech for this ephemeral memory.
Gain cell embedded DRAM is a strong contender mentioned in the paper. It offers better density than SRAM, but can be integrated on chip.
Use cases for STRAM.
Oh, lots. Think about the intermediate activation buffers in deep neural networks during training or inference. Those calculations generate massive amounts of temporary data that's used almost immediately and then discarded.
Right. Huge tensors that exist for milliseconds.
Exactly. Also, pointer chasing in complex data structures or temporary buffers like CFOs, message queues and servers, scratchpad memory, anywhere data flows in and out really quickly and doesn't need to persist.
So to make LtRAM and STRAM actually happen, we need these other memory technologies beyond just SRAM and DRAM.
Definitely. The paper points to this whole zoo of alternatives. Game cell EDRAM, FARAM, MRAM, RRAM, each one has its own unique profile. Different scaling roadmaps, different trade-offs, density, endurance, retention time, read-write energy, access speed. They're all different.
Crucially, they're not just drop-in replacements for DRAM or SRAM.
Not at all. They're specialized tools. You wouldn't use a hammer to turn a screw. Same idea here.
And the big lure for many of these is density, right? Getting more bits packed into less space.
That's a major driver. For instance, gain cell embedded DRAM, they estimate, can hit maybe 2-3 times the density of SRAM on the same manufacturing process node. That's huge for putting more cache-like memory right on the processor chip.
And RRAM sounds particularly promising for density.
It really does. It generally has lower read energy and latency compared to DRAM, and its cell structure is super simple. Basically a resistor, maybe with one transistor, sometimes just the resistor itself. That simplicity allows for incredible density scaling.
The paper has that striking comparison in Figure 2.
Yeah, it shows planar RRAM. It's just a flat layer, could potentially double DRAM density. But the real excitement is around 3D RAM, often called VRAM, where you stack layers vertically.
Like 3D NAND flash.
Kind of, yeah. And those architectures could reach up to 10 times the density of even the most advanced HBM4 planned today.
10 times? How?
Because VRAM can potentially stack many more layers, maybe up to 64, compared to HBM, which is limited by die stacking, maybe 16 or 20 dies practically. It's just a fundamentally more scalable structure for density.
Okay, but if these things are so dense, why not just use RM for everything? There's always a catch, right?
Always a catch. And this is absolutely critical to the paper's argument for specialization. These emerging memories, despite density wins, have limitations. RRAM, for example, often has limited write endurance. You just can't write to it millions or billions of times like DRAM or SRAM, and its write operations can be slow and energy hungry.
So no good for frequently changing data.
Absolutely not. You'd wear it out. Similarly, gain cell RAM, while dense, still needs those refresh cycles, maybe even more frequently than G in some cases. So you can't just swap them in.
This is why you need specialization.
Precisely. It forces you to match the data's behavior. How often is it written? How long does it need to stick around with the memory cell's specific strengths and weaknesses? You build a system using a mix of technologies, each playing to its strengths.
Okay, let's make this more concrete. How would this specialized approach actually change things in real-world systems? The paper gives examples.
Yeah, let's take some common server workloads. Think about things like in-memory databases or caches, Redis, memcached. They often have data that's read a lot, but its lifetime varies. Some stuff sticks around, some is short-lived.
So mix.
A mix would be ideal. LtRAM for the stable key-value pairs, STRAM for session data, or temporary computation results.
What about logging or system telemetry? Lots of writes, right?
Mostly write once, actually. You append data, but rarely read it back immediately, and maybe it only needs to live for minutes or hours before being archived off. That sounds perfect for STRAM's strengths.
Search engines, like Elasticsearch.
Interesting case. They have those huge inverted indexes, massive data structures that are read constantly to find documents. That screams LtRAM.
Okay. But then processing a user's query.
That generates lots of temporary data structures, scores, lists. Very short lifetime. Classic STRAM territory.
Even something like serverless computing, functions spinning up and down.
Perfect STRAM use case. Those execution environments are incredibly ephemeral. Code and data might only exist for seconds or even milliseconds. No need for long retention. You need speed and low active energy. STRAM fits the bill.
And you mentioned code pages earlier, stored in the actual program instructions.
Right. Super read intensive, lives forever basically. Putting that in LtRAM instead of energy-hungry dark. DRAM makes a ton of sense from a power and cost perspective. DRAM is often overkill for that job.
Now let's pivot to AI and ML. This feels like where the specialization concept could really shine, especially for our audience.
Oh, absolutely. AI workloads, while complex, often have surprisingly predictable memory access patterns. But ironically, these patterns often clash with the assumptions built into traditional random access memory like DRAM.
How so? Let's break down inference first. Running a pre-trained model.
Okay. In inference, the model weights themselves are usually fixed, immutable. You load them once, and then you just read them over and over again, often with very high bandwidth requirements.
Sounds like LtRAM again?
Textbook LtRAM case. Using standard DRAM or HBM for this is often wasteful because you're paying for write performance and endurance that you simply don't need for the weights.
And the calculations during inference, the activations?
Those intermediate results,
Ah.
they're generated, used almost immediately in the next layer's calculation, and then boom, discarded. They have incredibly short lifetimes.
Perfect for SRAM.
Absolutely perfect. High throughput, low latency, but no need for long-term storage. STRAM could handle that much more efficiently than spilling everything out to DRAM.
Okay, what about training? That's much more write-heavy.
It is, but it's still structured. You still have the model weights being read frequently, LtRAM candidate. But then you have the gradients being calculated in accumulator states for optimizers. Those are very write-heavy.
So maybe DRAM or even STRAM for those.
Potentially, but critically, the activation data during training behaves similarly to inference. It has very distinct temporal locality. It's hammered during the forward pass, hammered again during the backward pass, and then it's largely irrelevant until the next training iteration.
So even with writes, the lifetime is short. Still looks good for STRAM.
Exactly. Capturing those activations in STRAM could save enormous amounts of energy and potentially cost compared to constantly writing them out to and reading them back from main DRAM.
The specialization idea even drills down into the processor core itself, doesn't it? Affecting the caches.
It does. Think about what actually lives in the L1, L2, L3 SRAM caches most of the time. Function call stacks, local variables inside a function, intermediate results of calculations.
Stuff that doesn't stick around long.
Right. Most of it persists for very short durations, microseconds, maybe milliseconds. Our current large SRAM caches are often, in a sense, over-provisioned for retention for this kind of data.
So STRAM could potentially replace some SRAM in the cache hierarchy.
It's a possibility explored in the paper. STRAM, particularly gain cell EDRAM, could offer similar performance for this short-lived data, but at significantly higher density and with lower static power leakage than SRAM. Maybe not L1, but perhaps parts of L2 or L3 could transition.
Okay, this all sounds incredibly promising, but it's a huge shift. It's not just plugging in new chips. It changes everything about how we design memory systems.
Yeah.
The paper talks about major research challenges, right?
Oh, yeah. This isn't easy. It surfaces some really deep, difficult systems problems we need to solve.
First hurdle, abstractions. How do we even tell software about these different memory types without making programming impossibly complex?
That's maybe the biggest challenge. For decades, systems have worked hard to hide the complexity of memory hardware behind this simple, uniform view. A flat, byte-addressable space where performance basically just depends on how close the data is.
But LtRAM and STRAM break that model. Performance depends on what kind of memory it is, its endurance, its retention.
Exactly. So how does the operating system or the compiler or the application itself leverage these different characteristics? How do you expose things like retention time limits, write endurance limits, or the fact that reads might be way faster than writes without totally overwhelming developers?
It's a balancing act. Performance versus programmability.
A very delicate one. You need abstractions that are expressive enough to allow optimization, but simple enough to be usable.
Then there's data placement. If we have these different memory tiers, what data goes where and when?
Right. Our current memory management is pretty coarse. We move whole pages of data, like 4 KB, around. That's likely too crude for fine-grained specialization between STRAM and LtRAM.
We need to know more about the data itself.
We do. We need lightweight ways to profile data in real time. How long does it typically live? How often is it read versus written? What's its access pattern? And we need to do this without adding a ton of overhead that kills performance.
Could compilers help? Maybe developers add hints.
That's part of the solution space. Compiler analysis, maybe annotations, perhaps even special instructions could help guide placement. You need flexible frameworks. Some applications, like databases or ML training loops, might want explicit control. For others, you want the system to manage it transparently.
And getting the placement wrong, that could be bad.
Potentially worse than just slow performance. If you place data that needs to persist long-term into STRAM with limited retention, you could actually lose data. Reliability becomes a factor, not just speed. Predicting future access patterns accurately becomes critical.
Okay, challenge number 3. Coherence and consistency. Keeping data correct across all these different memory types with different speeds and characteristics.
Another thorny one, our existing cache coherence protocols, which ensure all cores see a consistent view of memory, mostly assume memory access times are roughly similar. That assumption breaks down with LtRAM and STRAM.
How does SRAM's limited retention mess things up?
Well, if a cache holds a line of data that originated from STRAM, the cache controller needs to know that the underlying STRAM copy might forget the data soon. Does it need to proactively write the cached copy back? Does it need to refresh the STRAM line periodically? Or maybe, in some cases, you could even allow the cached copy to become slightly stale if the application can tolerate it, just to save energy.
Tricky. And LtRAM slow writes.
That poses challenges for traditional coherence protocols, too. Many protocols rely on invalidating copies in other caches when a write happens. But if writes to LtRAM are very slow and expensive, maybe invalidation isn't the best approach. Perhaps update-based protocols, where you send the new data directly to other caches, become more attractive for LtRAM regions. Or maybe you separate the coherence tracking information from the data itself, keeping the tracking fast, even if the data lives in slow LtRAM.
It sounds like we might need entirely new protocols.
Quite possibly, especially for complex cache hierarchies that might span SRAM, STRAM, and LtRAM. Maybe things like message passing between cache levels become necessary to maintain correctness without killing the performance benefits of specialization.
And finally, we absolutely cannot ignore power and heat, especially with AI systems.
No way. You mentioned the numbers earlier, AI racks hitting 120 kilowatts now, maybe 600 kilowatts projected soon. Power isn't an afterthought anymore. It's often the primary design constraint.
And memory is a big part of that power draw, right? The paper has figure 3 showing this.
A huge part. DRAM alone can be responsible for something like 30% of the peak power consumption in a large data center server. That comes from leakage, those constant refresh cycles we talked about, and just the energy needed to move data on and off the chip.
So specialization is a power-saving opportunity too.
Massive opportunity. If you can put long-lived, rarely written data into LtRAM that has very low static leakage and doesn't need constant refreshing, you save enormous amounts of power compared to keeping it in DRAM. If you can handle short-lived, transient data in energy-efficient STRAM close to the processor, you save the power of constantly moving it back and forth to main memory.
But it's not just about the memory cells themselves.
No, it's a whole system problem. You have to co-optimize everything. The memory cell technology, the interconnects linking everything together, the packaging, and the software policies that decide where data lives. And when you pack things this densely, especially with 3D stacking like VRAM, cooling becomes a nightmare. We might need advanced cooling solutions, maybe even things like microfluidics integrated right into the chips.
Wow. Okay, so wrapping this up, this deep dive really hammers home that the memory scaling crisis is real, it's serious, and it's impacting everything, especially AI.
It's a fundamental bottleneck we have to address.
But this vision presented in the paper, this idea of LtRAM and STRAM, offers a really compelling, if challenging, path forward. It's about acknowledging that data isn't monolithic.
Exactly. Not all data is created equal, so why should our memory systems treat it that way?
This forces us to realize it's not just a hardware problem anymore, right?
Right.
Not just for the device physicists making the memory cells.
Not at all. It's a full-stack systems challenge. It requires collaboration all the way from material science through computer architecture, operating systems, compilers, and right up to the application developers. Everyone has a role to play in making specialized memory work.
So the final thought for you, our listeners. As you work with your AI models, as you design your systems, start thinking about the journey your data takes through memory. Where does it live? How long does it need to live? How often is it read versus written?
Could embracing specialization, moving beyond the traditional hierarchy, unlock unforeseen benefits in your own work? What new possibilities, or maybe even new complexities, arise when we truly tailor memory to the task? It forces us to fundamentally question not just how we store data anymore, but what we should expect memory to be.